All right, now we're in example 5 of section 8.3. Where in example 5, we're asked to give a formal proof that the series of n equals 1 to infinity of 1 over n cubed that we saw in example 1 converges. So we're going to use that integral test because it was just in our notes, so it makes sense that that is going to be the test we want to use. So before writing out the details of the formal proof, we want to first show some of our work. So we can say, let's consider the integral using f of n equal 1 over n cubed. So that would mean f of x, replacing n with x, would be 1 over x cubed. So let's look at that integral from 1 to infinity of 1 over x cubed dx. So this is what's called an improper integral because the bounds of those integration of our integration is not a finite number. So how do we deal with that? Well, we write this then as a limit, or we could use b goes to infinity of 1 to b of x, I'm going to say to the -3 because that's going to be helpful when we actually compute that integral. So just switching that x cubed in the denominator with a negative exponent. Okay, so what we need to do is take that antiderivative of our integrand. This might have been a couple weeks before you've done this, so it's okay to brush up here. And so the antiderivative here would be that we need to add 1 to that exponent, so x to the -2. And we're going to divide out by that new exponent, so we want to divide out by -2. And we're still looking here at the limit as b goes to infinity. So I need to back up here and make sure I include that notation. Very important. So this is the limit as b goes to infinity of, now I'm going to take that integrand. So this becomes what? This becomes x to the -2 over -2. We're evaluating at x equals 1 to b. All right, so what does that become? So I'm going to evaluate this antiderivative at my two bounds. So that'll look like the limit as b goes to infinity of, so I'm going to go ahead and rewrite this exponent as an x in the denominator. So it looks like 1 over, so negative 1 over 2 b squared minus negative 1 over 2 1 squared. Okay, so we're looking here at the limit as b goes to infinity. So here we just have a finite number. So that would just be 1 over 2. Here, as b goes to infinity, what happens to this term? Well, the denominator blows up, so this entire fraction goes to 0. So in taking the limit, this becomes 1/2. So we see that this integral here, this improper integral, converges. So let's go ahead and look at that integral test to see if we can apply it. Well, we are in this situation too, where that integral converges. So that means our series is also going to converge. So let's go ahead and write up that proof formally. So proof. We always start our formal proofs with the word proof. So now what do we know? Well, since the integral from 1 to infinity of 1 over x cubed dx, since that integral converges, we can even just say see work above. If we've made our work really clear using the proper notation, using the proper steps, we can summarize that by saying see work above. In that way, often if you're reading a math textbook, it says like is left to the reader, or maybe it's done in a previous example or section. Because this integral converges, the series from n equals 1 to infinity of 1 over n cubed also converges. And this is true by the integral test. All right, so there is our formal proof. And now let's just make sure we have everything that's needed in a formal proof. So let's check. Do we have complete sentences? Check. And we could have done more to include this work in our proof, but as long as it's in there, that's clear, then you can go ahead and just summarize your proof with one sentence like that. Do we have proper notation? So this means even in our work, we're making sure that whenever we have equals, it's true that that equality is in fact correct. So we're showing equality. Oh, we're showing justification why each equality is so. And even down here, when we rewrite the series using that proper notation, using sigma notation, and then also using our theorems or stating the theorems we use. Have we done that? Check, using the integral test. Awesome. So there you have it, a formal proof that our series that we met in example 1 converges.